Morning, everybody. Today we're going to go over something called the conservation of momentum. The conservation of momentum is mostly used for things that collide and bounce off of one another, but it can also be used for things that explode, things that stick together, and it's even used at the atomic level to calculate the speeds of atoms and nuclei. But we gotta crawl before we can walk, so we'll stick with the big stuff for now. We gotta define these three things first. They're pretty straightforward, but we need them for sure, so may as well go over them. We got internal forces, external forces, and then we have the actual conservation of momentum. Within these terms, there's something called a system. The system is basically the two objects that you're looking at, and the idea of a system will become most clear when we do an example at the end. So hold on to that confusion until we get to it. Here's what we have for internal forces. Internal forces are forces that objects within a system exert on each other. Forces that objects within a system exert on each other. So if you're looking at we're going to look at two train cars later. The two train cars hitting against one another and pushing off of one another, those are internal forces. But if you had somebody else or like an engine pushing on these things, those would be external forces. So external forces are forces exerted on objects. Forces exerted on objects by agents outside the system. So you always define your system when you're doing a momentum problem. And any object outside of that system would be considered an external force. And so with that, we can actually get to the principle of the conservation of linear momentum. So that's principle of conservation of linear momentum. Here it is. The total linear momentum of a system is conserved, which means that it remains constant as long as the sum of net external forces is zero. The total linear momentum of a system is conserved, and that means that it remains constant, as long as the sum of external forces is zero. And we could put that into an equation form as well. So the sum of linear momentum is the same before and after. We have this word sum that appears, and that implies that we're doing a sum. We have our sigma term that means sum. The sum of our momentum before is equal to the sum of our momentum after. So we're going to put our before symbol, our initial symbol. We're going to put our after symbol, which we do F for final. We'll put a box around that. Put a little asterisk because it's pretty important to have the sum of the net external forces is zero. So we'll write that mathematically as well. Whoop. There we go. As long as sum of F external equals zero. And that's all the writing I've got for this page. So this right here, this equation represents that whole definition. That's why I kind of flew through all of that to get to here. this is what we're going to be looking at most because we're going to be doing math with it. So what we have here is the sum of our final momentums is equal to the sum of our initial momentums, and we're going to expand this out and do a lot of math with this. Now, the coolest example I've heard really two really cool examples of conservation of momentum. The first is if you have an atom at rest, and the atom just explodes and goes in two different directions. You have an atom at rest, and if it's at rest, its momentum is 0. So when it explodes and moves outward, the sum of these two momentums, the two pieces of the atom, the sum of those will be 0. So one's positive, one's negative. They cancel each other out. I've also heard the same example with the Big Bang. So the theory of the Big Bang is that at the beginning of time, our universe was at rest, and it was in the form of a tiny little dot. So the universe was just a tiny little dot. All the atoms were crammed into one space. The momentum of that is 0. And the Big Bang says that it all started to expand rapidly, spontaneously. So that means that all the momentum of all the stars in our universe add up to be 0. So some of the stars in our universe have a positive momentum, some of them have a negative momentum, and those numbers all cancel one another out to be 0. But let's break this down here. This is the important thing. We're going to use this to do some math. It's really easy to understand conceptually once you break this down. So we'll do a quick derivation to make that more digestible, more usable. And here's the derivation statement. Do a quick pause if you want to write it down. Expand the conservation of linear momentum to include M, VO, and VF for a two-object system. We're always going to use two-object systems, so this will be useful once we derive this equation. So let's look at both of these pieces. The sum of our final momentums. Well, if there's two objects, that means there's going to be, hold it. That means there's going to be two momentums at the end. So we'll expand that out. It'll be P1F plus P2F. And in this two-object system, there's two pieces before as well. So the sum of our initial momentums is those two momentums added together. So we've made it a little more descriptive. We've got two objects. Object 1 has an initial momentum. Object 1 has a final momentum. Object 2 has an initial momentum, and object 2 has a final momentum. So these two objects are colliding, causing each other to change speed, and because of that, they're causing each other to change momentum. They're transferring momentum between one another. The goal is to expand them to include M, V, and V initial and V final, and that's pretty easy. If you recall from last week, this is our momentum equation. You don't have to write it down because you've got it somewhere. So we're just going to apply that to all four of these little terms. P1F is M times V. Well, M1 times V1. P2F is M2 times V2. P10, again, it's M1 V1. P20 is M2 V2. We're almost there. The problem we have now is that there's two V1s and two V2s, so we need to differentiate between these. We got to put our initial and finals here. The mass of these objects is not going to change. In some cases, like really complicated college problems, your masses will change, but not here. We're going to be looking at like cars that collide, train cars that collide, people that collide, and when they do so, they're not going to change mass. So the thing that changes is their velocities. So basically all we got to do is we got to put initial over here. So now it's V10 and V20. And over here, it's V1F and V2F. So this is the number one thing that we gotta write down. Still, we need to remember it's as long as the sum of external forces is 0. The only forces that are allowed in these problems are these objects pushing on one another. The only forces that we can acknowledge are these forces pushing on each other. So that's the number one thing. Don't get too caught up in all of the conceptual stuff that we did over here. Write it down, but don't get yourself confused by it. The number one thing is making sure you understand all these letters. M1V1F, so that's kilograms and meters per second. M2V2F, kilograms and meters per second, equals M1V10 plus M2V20. We're going to use that to solve problems, and that's the number one skill I want you to have. Take a look at the next video. We'll do an example or two.